Okay, good morning everyone. Good morning. Great day to be learning heat transfer. Alright. So, we're going to move on to a new phase of heat transfer where we go into the nitty-gritty details of conduction heat transfer. Okay? So, conduction. Now we start getting a little nasty here in terms of the math. Maybe not today, but next course. What we have seen so far, we've seen introductory equations. Okay, we've seen equations for conduction which comes from Fourier's law. We simplified that and said we will look at a one-dimensional situation with a lot of other simplifications. And we looked at convection heat transfer using some basic equations, Newton's law of cooling, and then radiation heat transfer under a whole host of assumptions, right? So we looked at all these three things and then we solved some problems just to get ourselves juiced up and get ready for the battle ahead, okay? So now we go into conduction heat transfer, and I just want to remind you that conduction requires that there be no bulk motion, okay? So it's constrained by that. So no bulk motion. And conduction is essentially the transfer of energy due to molecular interactions. We've spoken about this before, okay? So energy transfer due to molecular interactions. It can take place in solids, it can take place in fluids, fluids meaning liquids and gases, as long as there is no bulk motion. The law that allows us, or the equation that allows us to understand conduction, bear with me while I close the door. Won't let any heat go out. Okay. So the law that enables us to study conduction heat transfer is Fourier's law. This is a phenomenological law, which means it is experimentally observed. There is no theoretical proof. Okay. So Fourier's law. And essentially, I'm going to write the vector equation, vector form of this. It says that the conductive heat flux is proportional to the negative of the temperature gradient. So Q double prime. Notice from now on, I'm not going to add the subscript conduction. It is implied that we are studying conduction. Okay? So Q double prime vector is equal to minus K times the gradient of the temperature, del T, where the gradient operator, I'm going to start off problems in the Cartesian system first. So in the Cartesian, if I expand that equation, we end up getting the following. You've seen this before, this is nothing new. We've written this in the past. Q double prime x I hat, where I hat, j hat, k hat are your typical unit vectors along the Cartesian system. Q double prime y, j hat, Q double prime z, K hat, this is minus K. We are assuming that the thermal conductivity K is isotropic, which means that it has no directional preference within the material. Okay? It could be a function of space and it could be a function of x, y, and z. That is completely fine. All I'm saying is it does not have any directional preference. It's not greater at 45 degrees to the x-axis and lesser at 92 degrees to the z-axis. That doesn't happen. That's what is meant by isotropy. For the time being, I'm going to assume it to be a constant. So this is minus k dt by dx dt by dy dt by dz k hat. Okay? T is a function of space and time. And we can also point out a few things. This is something that I also mentioned some time back when we looked at conduction. The direction of conduction heat transfer is parallel to the normal of the surface area for a surface that has a constant temperature. I want to clarify this statement now. Okay, so suppose I have a slab of, whatever, brick or something, slab of clay. Okay, so this is a slab of clay. Let me assume that heat transfer is one-dimensional. We're going to be focusing mostly on 1D for the time being. 1D heat transfer. Let's assume that heat transfer is taking place from the left to the right. Okay, so Q double prime. This is the direction of heat transfer. If I focus on the surface at the left or the surface at the right, it does not matter, it's equally the same. On this surface, what we are implicitly assuming when we are doing one-dimensional heat transfer is that at any point on that surface, the temperature is the same at that x location. Okay, so if I call this as x is equal to some x plus dx, and this is some side x, then at x is equal to x plus dx, I'm assuming that at all points on that surface, the temperature is just the same. T of x plus dx comma t. It's a multivariate function of space and time. A surface whose temperature is a constant is called as an isothermal surface. You've come across this term in thermodynamics. So this is an isothermal surface. And so this tells us a very important point. The direction of conduction heat transfer is along the normal to an isothermal surface. It's left or right or right or left, I don't know, it depends on temperature distribution, of course. Okay, but the main point, the underlying point is that the direction of Q double prime is normal to the isothermal surface. So Q double prime directed normal to isotherms, which are lines of constant temperature. And if you want, you can draw a normal here. N hat is the normal. And the direction of Q double prime is along N hat. Alright. So this is not to belabor this point, but we've seen this before. What do we want to do in conduction? What's new? Of course, we can't prove Fourier's law. We can prove it experimentally. That's no good. We're going to take it as a matter of faith. Okay? Repeated observations without any exceptions. What we're going to do is we're going to make use of Fourier's law and then understand how heat transfer takes place within a control volume. And this is represented by what is called as the heat diffusion equation. Okay, so we're going to derive this From now on, my shorthand term is HDE, heat diffusion equation. So this tells us how heat transfer is taking place within a control volume. How conduction takes place within the control volume. And this could be in the absence or in the presence of unsteady effects, so temperature is a function of time. Which means that your E dot CV is no longer 0. And then it could also be in the presence of energy generation. Okay? My aim, whenever possible, is to make sure that these derivations are as painless as possible. So from that perspective, the derivations that I do will be slightly non-rigorous. They are nevertheless true, cannot dispute that. If you look at the book, it will be a little more complicated, more overwhelming. But if you understand what we do in lecture, it is as good as doing what is there in the book. Okay? Alright, so I'm going to do this heat diffusion equation derivation for one dimension, and then we will generalize this for 3 dimensions. It's not very, it's very fairly simple to generalize this for 3D. So assume 1D heat flow let's assume that this the x direction is the direction of heat flow. Okay, so x left to right or right to left, it is just the horizontal coordinate. Okay. I'm going to assume that the thermal conductivity is isotropic, material is isotropic, sorry. The thermal conductivity can be a function of the spatial variable, but it has no preferential direction. Okay, so K could be a function of x, but it has no preferential direction. Okay. We're going to assume for the derivation purposes that the heat generation is positive. If it is negative, just put a negative sign. No big deal. Just for simplicity. Okay, it does not do anything to your life if you assume it to be negative. And I'm going to assume that unsteady which means that E dot stored is not 0. Under this situation, I want to see what's happening within the body. Okay. So I'm going to take the same brick and draw it out here. Some solid body, thermal conductivity, let's say, is K. Within this solid body, I'm going to look at an infinitesimal volume element, something similar to what you would have seen in mechanics of materials. You draw volume elements there. I'm just going to grab a small piece of volume, draw it out. Okay? So volume element in the form of a cube. Okay, so this is dV or delta V. Infinitesimal volume delta V. Okay. And this is essentially, I'm going to take that out, draw out its geometry. Okay, so this is the control volume, And let's see if I can draw some dotted lines on it. Okay. Now what we are saying is that along the x-axis, so x, y, and z axis, I have to draw that first. X, y, z, heat direction of heat transfer is along the x-axis only. We are assuming that the y and the z surfaces are insulated. Okay, there is no heat traveling through those directions. This is some volume. Okay, so this is at some location x. And if I say that the thickness along the x direction is delta x, this is location x plus delta x, so the thickness is delta x. Then some location y along the y-axis, and this is going to be location y plus delta y, so that the height is delta y. I'll label that out as well. And likewise z and delta z. Okay, so I call that as z. This is z plus delta z. So this is delta z. Okay, so this is z plus delta z. I just ran out of some space to write it out. Direction of heat transfer is along the x direction. So the area that I'm interested in is going to be the shaded area here. I'm going to call that as delta A. And it is quite obvious that delta A is delta y times delta z. That, as you can see from the figure. Okay? So delta A is delta y times delta z. What is the volume? Delta V is delta A times the thickness delta x. Which is delta x delta y delta z. So these are the geometric properties of this infinitesimal volume element. Now I'm going to draw the 2D view of this volume element. Okay, so which means essentially I'm going to draw this face here, which is projected towards you. Okay. There is heat generation within, so E dot G is not 0. It is unsteady, which means that there is variation of temperature with respect to time, so E dot stored is not 0. I want your help now. What is the variable that depicts the transfer of energy into the control surface here? On the left side.
From the inner surface on the left.
It has to be the conductive flux. Why is that? Why there is no mention of convection and radiation here? Because I'm taking this volume element from within the body. Okay, so keep that in mind, and thank you. I'm going to call this as Q double prime at location x. This is x plus delta x at location x. And then, of course, whatever heat goes in has to come out, no matter who you are. Q double prime x plus delta x. All right. Now we are going to write the thermal energy stored at a point in time t. So E stored, not dot, just E stored at time t. This is the thermal energy stored at a time t. It's typically with respect to a reference temperature. You would have seen this in thermodynamics. I'm not going to derive these things here. Okay, we're going to take it for granted. This is m times c times t as a function of x at time t minus some standard reference temperature. It does not matter what it is, depends on your measuring instrument as to what you want that reference temperature to be. Okay? M is the mass. Mass of the body, okay, which is the control volume here. So this is rho times delta V. Simple enough, right? C is the specific heat capacity. You would have come across this creature in thermodynamics many, many times. Okay? This is the thermal energy stored, not the rate. So I just want to make sure there is no dot there. It looks like, oh, great. Thermal energy stored at time t. Specific heat capacity, of course there will be this confusion in your mind, okay, is this guy talking about specific heat at constant pressure or at constant volume? That's a very valid question to ask. We're going to assume incompressible medium. Which means that the specific heat at pressure, constant pressure and volume are the same, so Cp is the same as Cv. We just call it C. What do you do in case of a compressible medium? We don't deal with that in this course, but if you do, experimentally validated that Cp is a better choice than Cv. Okay? But we're not going to deal with that. Stored energy at T plus dt or delta T. Exactly the same expression, but the temperature is at delta T. So this is m times C T at x and T plus delta T minus T reference. And I'm going to write down E dot stored now. E dot stored, looking at finite length, okay, not infinitesimal as yet, but looking at finite length, I can say this is E stored T plus delta T minus E stored at T divided by delta T. Some average change in the stored thermal energy, okay, over a time interval delta T. And obviously we have all our equations here. If I substitute and go through the math, this is fairly trivial to show. E dot stored is mc T at T plus dt minus T at T. mc minus divided by delta T. By the same token, the energy generated, we looked at this special term last time, the volumetric energy generation, so Q dot, little q dot, times delta V, which is Q dot times delta X, delta Y, delta C. Alright, so we have all these things. We're almost there. All you do is write the first law. First law for thermodynamics, but written from the perspective of ME 4510. So first law, E dot in, E dot out, E generated, is E stored. We are assuming positive heat generation, so you can just say negative heat generation and put a negative sign, no harm done. E dot in is the conductive heat flux multiplied by the surface area. So this is Q double prime at X times delta A minus Q double prime at X plus delta X times delta A E dot generated is Q dot, and I can write that as Q dot times delta A times delta X if I want to make a quicker note. This is E dot G equally valid, okay? So this is delta X, delta A, this is equal to E dot stored, which we just wrote down, the giant expression there. Instead of mass, I'm going to write the density times the volume. Instead of the volume, I'm going to write it as area times the thickness. So this is going to be rho delta A delta X, which is delta V, specific heat capacity C, and then I'm going to have T plus delta T, all of this divided by delta T. Let's take a deep breath and cancel off the delta A on all sides. Okay? And you immediately should be seeing where we are going with this. I'm going to take this delta X guy and spread its goodness on the left hand side. And if I then start taking limits, as delta X and delta T go to 0, I will end up with differential quantities, which tells me that this is valid, this equation that we are deriving is valid no matter how tiny your control volume is. Okay? So at a material point within the body, this equation is valid in some sense. Alright, so I'm going to rearrange this term and write it as minus Q dot at X plus delta X minus, Q double prime and X. I'm dividing through by delta X, so divided by delta X. Q dot, nothing more there. This is equal to rho times C, because I'm dividing through by delta X, so that's gone. So rho times C, T at X and T plus delta T minus X and T, delta T. Take limit delta X tending to 0. Negative sign from there. Okay, so just rewrite the following on the top. Q double prime plus Q dot. Now you are shrinking the time period as well. Not only are you shrinking the length of the volume element, making it a material point, you're also shrinking the time. So this becomes an instantaneous quantity rather than an averaged quantity. So this is now going to be limit delta T tending to 0, rho times C, all of that divided by delta T. I'm just rewriting the previous line, just taking limits on both sides. Okay, nothing special going on. Left hand side, remember there is a negative sign, but this first big term becomes the partial derivative of Q double prime with respect to X. Why is it partial derivative? Is because Q is a function of temperature. Temperature is a multivariate quantity. It's a function of both space and time. So I can only talk about partial derivatives because this is derivative with respect to space. So on the left hand side I have minus dq double prime by dx as a function of x. Don't forget the quantity k, which I forgot here. Oh, well, not yet. They will come soon. Plus Q dot. And likewise, rho times c is a constant, does not get affected. And I'm going to have limit of t minus t at two different time instances divided by delta t is dt by dt. dt by dt. The partial derivative of temperature with respect to time. Temperature here is a function of x and t, which is why we are taking partial derivatives. Now we bring in Fourier's law, q double prime is minus k dt by dx. And then I do the substitution and I write the most general form of the heat diffusion equation for 1D. Okay, so most general form. Heat diffusion equation minus d by dx of minus of k times dt by dx. The negative sign here combines with the negative sign there and they become history. So I'm going to have d by dx of k dt by dx. This is for 1D, so I need to mention that. Plus q dot is rho times c dt. And that's it. We've done pretty much all the derivations for the next few weeks. And all we're going to do is exercise this equation in multiple scenarios in a practical situation. Okay? But before that, some caveats. Suppose k is a constant. K being the thermal conductivity of the material property. I can take k out of the differentiation, so I'm going to end up having k d square t by dx square, right? Because d by dx of dt by dx is d square t by dx square, second derivative with respect to space, plus q dot. That doesn't have anything happening to it. Rho times c dt by dt. Equal here. And sometimes people write it also in the following manner. Take that thermal conductivity, divide through, and I'm going to skip and say okay, I'm just dividing through by the thermal conductivity. And now we define a new term called thermal diffusivity, alpha. Thermal diffusivity. This is the bread and butter of people who do conduction heat transfer. It is a ratio of the tendency to conduct heat divided by the tendency to store energy. Rho times c is a function of how much energy is stored, density times specific heat. Okay, so this is tendency to conduct heat which is what is represented by the thermal conductivity. Higher the thermal conductivity, greater the tendency to conduct heat. And rho times c is the tendency to store thermal energy. You'd have come across the term thermal capacitance when you did system dynamics at some point. You'll see those creatures coming into life again. Okay, so if I rewrite this equation, so 1D constant K, E dot generated is positive, I'm assuming, okay, so say E dot stored is not zero, so this is unsteady. the heat diffusion equation for one-dimensional flow can be written as d square t dx square q dot by k is 1 by alpha. Notice that rho c by k is 1 by alpha dt by dt. And so you would have heard the term diffusion of heat. Right? What's the difference between conduction and diffusion? There is a very thin line separating the two. Diffusion can be categorized as any general heat transfer, but we are studying it from the perspective of conduction. So one way of thinking about diffusion is it is similar to unsteady conduction. Conduction in the presence of change in the stored energy within the control volume. Okay? Alright, so I'm going to do one thing, and you're going to do another thing as an in-class quiz, but this will be submitted by you on Wednesday. I'll just write down the quiz problem. It's it's a really trivial, you'll see that at the end of the day. I'm going to derive the temperature profile. Okay, so before I do that, I think I'm getting ahead of myself. Why are we doing these things? What's the purpose of these equations? One purpose could be the following. Suppose I experimentally determine, using thermocouple measurements and so on, here is the temperature profile through this medium. Then using that temperature profile, I can calculate any kind of a quantity. For example, if I need heat generation, I can calculate that. Or if I have certain conditions that are met, I can find out how the temperature is evolving as a function of time. This is a partial differential equation. Its solution is non-trivial. You will have to use numerical methods. Okay, so that's one thing that we can do. The other thing which is more relevant to us is, okay, I'm given this body, some slab. I know the temperature distribution on one side, I know the temperature distribution on the other side. Perhaps I am generating heat within the body through means of electrical wires, or maybe some kind of a reaction whose details are all known to me. Can I come up with the temperature distribution? That is the problem that we will be spending a majority of time solving. And what we will also do further to simplify your life and my life and make it a great life is we will say that temperature is not a function of time. So we are first going to look at steady conduction in the presence of energy generation. Okay? So that's the first thing that we're going to do. But in general, to solve this kind of a problem, this PDE here, this is a partial differential equation. You need three things for this partial differential equation. This is a 1D PDE. Because it's a function of only one spatial variable, it's a function of time as well. It's a 1D unsteady partial differential equation. You need three things. You need an initial condition, because of the fact that the dependence on time is a first order dependence. Okay, so first order, that is the PDE, this partial differential equation has a first order time quantity here, which means that I need an initial condition to be prescribed to solve this problem. What you would have done in system dynamics is you would have solved only ordinary differential equations, and they are all time dependent quantities, which means you will have to deal exclusively only with initial conditions, displacement condition, velocity condition, and so on. In our situation here, it's a little more complicated. It is not only a function of time, it's a function of space as well. So to have the time dependency taken care of, I need an initial condition. So this is at some time Ti, the temperature is T is equal to Ti. Okay? But it has a second order dependence on space. right? Because it's d square t by dx square, which means I need two boundary conditions on top of the initial condition. Boundary conditions, my shorthand notation is BC from now on. And so look at how non-trivial this problem becomes in 3D. I need one initial condition for time in 3 dimensions, because time is only a single dependency, even in 3D. But for each spatial dependence, x, y, and z, I need 2 boundary conditions, which means I need 6 boundary conditions, 1 initial condition. Life is a pile of misery. You cannot solve those equations by hand. You have to use numerical techniques. Okay? These boundary conditions can be prescribed in 2 manners. One manner is where you prescribe the temperature on the 2 surfaces. So we are doing 1 dimensions, right? So keep that in mind. So boundary conditions. I can prescribe temperature at x and temperature at x plus dx. T at some x is equal to 0, some x is equal to delta x. Okay. If I prescribe temperature on the boundaries, then this is called as a Dirichlet boundary condition. I need 2 boundary conditions for 1D. Okay, once again we are restricting to 1D. But there is no need for me to specify 2 temperature boundary conditions. I could specify 2 flux conditions. I could specify these. For example, I could say that my surface is insulated. Last class we found out that if you have an insulated surface, the flux at that surface is 0. If I prescribe the derivatives as the boundary condition, the first derivatives as the boundary condition, this is called as a Neumann boundary condition. Most problems will be a combination of the 2, so they will be called as a mixed boundary condition. You either prescribe temperature at a surface, flux at a different surface, or vice versa. Okay, so that's what we will be dealing with. Okay. So I guess we have some time left. Eyesight is not as good as it was before. 15 minutes left, so we'll get a crack at the problem. But before that, I want you to find out the following. As an in-class quiz, you'll do this and upload it before class on Wednesday. Okay? So in-class quiz 1. So due before lecture on Wednesday. Let us assume the following situation. 1D, no heat generation, steady situation, if I have a situation of this sort, what do you think the temperature profile is going to be through the body? Linear. All you have to do, very simple, very trivial, take the heat diffusion equation, then the temperature profile is linear. And this is essentially what we spoke about at the beginning of the semester. Now we have the mathematical tools to actually prove what we were talking about. Okay? And I'm going to do something a little different or better than this. A little better in the sense that it's more complicated, but not as complicated anyways as numerical solutions, which I'm sure you love from 2815. So, I'm going to consider the situation of steady conduction, but in the presence of constant energy generation. So 1D, E dot stored is 0, so I'm assuming steady, one dimension, and I'm assuming that Q dot is a constant. What could be the temperature profile? Temperature profile across the body. Okay, so this is some one dimensions, right? So I'm considering at location x plus dx. I'm assuming that Q dot is a constant. And I'm going to deal with the heat diffusion equation. Start off with this guy. So the standard form, we write d square t by dx square, x comma t. So I'm going to say this is the x-axis, x comma t by dx square plus q dot. This is equal to rho times c by k dt by dt, or 1 by alpha dt by dt. Both of them are the same. I'll just be consistent and write this is 1 by alpha. This is the heat diffusion equation. This is the general one. We are assuming steady, which implies that dt by dt is 0. Which means now my partial differential equation becomes an ordinary differential equation, because it is now a function of only the spatial variable x. So this is gone, and so I have d square t of x y dx square. Look at this, I go from partial to a full derivative, so ordinary differential equation plus q dot is equal to 0. Q dot is a constant, so I can bring it on to the other side. So, d square t by dx square is minus q dot, which is a constant. Integrated once on both sides. Question?
Should be divided by k.
Divided by k. Yeah, thank you. Yes, absolutely. Thank you. But k is also a constant, so that's one big constant. But anyways, we'll keep it. I integrate it once, I get the following. Minus q dot by k times x plus some constant c1. Integrate it one more time. I'm assuming you've come across differential equations of that following sort. Just integrate it twice. It's just a function of one spatial variable. Be careful if there are functions of x on the other side, which we will deal with in the next lecture. So this is now t at x, or t of x. T as a function of x is obviously a quadratic. So this is for steady, constant heat generation. And I had posted a problem at the beginning of lecture. That problem essentially employs this kind of a temperature profile. It's a quadratic temperature profile. Okay, so I'm going to go to my problem now, or a parabolic distribution. So let's go to the problem that we have. This is similar to what you are supposed to be doing in your in-class quiz. Not any different. Obviously, if q dot is 0, then you know the answer, it is linear. Okay, it is the way it is. Okay. So I have the problem from what we posted. Given T of x is 200 minus 2000 x square. Immediately, if you see a parabolic distribution of temperature within the body, the heat generation is a constant. No questions, no doubts about it. We've just proved it. Okay, so this implies volumetric heat generation is a constant. Is it positive or negative? We don't know. Okay, so that's the question here. You're told that this is the temperature profile through a solid brick. Okay, I'm not going to draw that yet. Thermal conductivity is given to me, thickness is given to me. 50 mm, and then K, 50 watts per meter Kelvin. Determine Q dot and steady conditions. Obtain Q dot, and we will also sketch the temperature profile. And what we will be doing from now on is, without using a computer, without using a calculator, just by looking at the temperature equation profile, we need to know how to sketch the temperature profile. Okay? Q dot, it's fairly trivial because I already have this equation. So from what we did, 1D steady state minus Q dot by K. D square T by dx square. T is known as a function of x, so this is d square by dx square of 200 minus 2000 x square is minus Q dot, which I don't know, divided by